the most important but the most incompletely understood concept in all of science. Having illustrated in part 1b the second law of thermo for an isolated system using the spontaneous heat flow process, let us first rationalize in this part 1c why delta S isolated system is always positive for the heat flow process. There is an elegant explanation from a mathematical point of view. According to Clausius, as seen in part 1a, ds equals d/q reversible over Kelvin T. A reversible process is one during which an infinitesimal amount of change occurs at every stage of the process. Let us say that at every stage I, an amount of heat equal to d/q flows from the hotter one to the colder one, causing an infinitesimal amount of change in S, namely dSi in each. Since the hotter one releases heat, its d/q is negative and it is positive for the colder one which absorbs heat. T of the hotter one is higher than that of the colder one at every stage until they both become equal at the equilibrium state. Since the value of a ratio is larger when the denominator is smaller, at every infinitesimal stage of the reversible process of the heat flow, the magnitude of the positive dSi of the colder body is larger than that of the negative dSi of the hotter body. Their sum, which is determined using the definite integral from either initial T hot or T cold to T equilibrium, is then necessarily positive. That is, the net delta S for the whole process undergone by the isolated system is necessarily positive. The same kind of mathematical analysis shows why the heat flow does not continue after the temperatures of both the hot and cold bodies become equal. Let us assume a flow of an amount of heat equal to d/q from the original hot to the original cold body. As a result, the former becomes colder and the latter becomes hotter. In the next stage of heat flow, the magnitude of the negative term becomes larger than that of the positive term, since the denominator of the negative term is now smaller. Therefore, their sum is necessarily negative, implying the total entropy decreases. The same is the effect for the ensuing stages also. If the natural tendency is for the total entropy to increase, then this continuation of heat flow goes against it. And of course, the natural tendency is for the total entropy to increase. That's why it does not continue. Hence, the first part of the mathematical statement of the second law regarding any spontaneous process of heat flow from hot to cold, which says delta S total is always positive for such a process. The above is true for any spontaneous process, whatever it might be, even in a closed system. In other words, the increase in entropy of one component, either the system or the surroundings, always more than compensates for the decrease in entropy of the other, so that the net change is always positive. This has an important consequence in chemistry. Whenever two atoms combine together to form a chemical bond between them to produce a molecule, entropy always decreases, as will be discussed in detail in part 2 of this video series. Since nothing escapes the long arm of the second law of thermo, the only way this process can ever occur spontaneously is that the entropy of the surroundings must increase. It can never ever occur in an isolated system. It can only occur in a closed system. How can the entropy of the surroundings increase? The combining atoms must release heat to the surroundings, and the latter must absorb it in order to increase their entropy. This implies that the formation of the chemical bond should always be exothermic in nature. It is a grave misconception, especially on the part of some biologists and biology textbooks, that bond formation is endothermic, that is, atoms absorb heat when they combine together. It is also critical that the increase in entropy of the surroundings is larger in magnitude than the decrease in entropy of the combining atoms, so that the net change is positive, as seen in the case of hydrogen atoms combining together to form H2 molecules at 1 bar and 298 Kelvin. The change in entropy of the system is negative 12.744 joules per Kelvin mole, and the corresponding change in entropy of the surroundings is positive 1.46 times 10 raised to 3 joules per Kelvin mole, such that their total is positive 1.45 times 10 raised to 3 joules per Kelvin mole. If the two atoms in question cannot satisfy this condition, they cannot bond together at all, lest such a bonding should violate the second law. The above also has an important consequence in the case of heat engines, which always have to operate between a hot source of heat and a cold sink, where one portion of the heat absorbed should be dumped after converting the other portion to work. Since the change in entropy of the hot source is negative, there ought to be a mechanism for a positive entropy change whose magnitude is larger than that of the negative entropy change. This latter is provided by the cold sink. Thus, no heat engine can ever operate only by absorbing heat from a hot source and converting all of it to work. A cold sink is always needed so that the second law is not violated. In other words, all heat engines always operate between two temperatures, never using only one high temperature. Secondly, why does W always increase as T increases, as seen in tables 2 and 4? As the temperature increases, more and more energy becomes available from the surroundings for the particles at the lowest energy level to absorb and get excited to higher energy levels, and they do so. As a result, N0 decreases and the other Ni's increase, as seen here in the case of silver, for example, which is also noticed in table 1 for lead. In other words, the populations at the higher levels increase at the cost of the population at the lowest level. The effect of decrease in N0 factorial in the denominator of the equation to calculate W is to increase the value of W, and that of increase in each other Ni factorial is to decrease the value of W. However, the decrease in N0 is always greater than the increase in any one particular Ni value, because the decrease has to equal the sum of all the increases. Therefore, the effect of N0 on W is greater than that of the other Ni's, as seen in the example of N equal to 160. And in addition, a decrease in a larger value in the denominator has a greater impact on the ratio than an equal increase in a smaller value in the denominator, as seen in the example of N equal to 15. The net effect is that the value of W always keeps increasing as T increases for any given system of particles. Incidentally, when the populations in the occupied levels become equal, the corresponding temperature happens to be infinite with the largest value for W and hence the highest value for S entropy. This even dispersal or spreading out of energy is the limit toward which the distribution at absolute zero, where all the particles are concentrated at the lowest energy level and hence energy is localized, keeps moving as the temperature increases. And W and hence S keep increasing and reach their maximum values at infinite temperature. For example, if there are 100 particles in a two-state system for which only two non-degenerate energy levels are allowed, at absolute zero, all of the 100 particles are concentrated at the lower energy level. As the temperature increases, more and more particles get excited to the higher level. The limit, namely infinite temperature, corresponds to 50 particles in each of the two levels. In case we force further excitation by supplying energy, the result is called population inversion and corresponds to negative Kelvin temperature, as can be algebraically seen from the Bottzmann distribution equation. Using the Clausius definition of entropy change, one can derive a relation between change in temperature and the corresponding change in entropy. When the volume is kept constant while heating or cooling the sample of matter, delta S equals N CVM ln of Tf over Ti, and when the pressure is kept constant, it is N CPM ln of Tf over Ti. Here, CVM is the molar heat capacity at constant volume and CPM is the molar heat capacity at constant pressure. An algebraic analysis of either equation indicates clearly what happens to S as T increases. In both equations, when T final is higher than T initial, the ratio is greater than 1, for which the natural logarithm is always positive. N, R, and C are all always positive, and therefore delta S is positive, which means S increases. When T final is lower than T initial, the ratio is less than 1, for which the natural logarithm is always negative, making delta S negative, implying S decreases. It is very difficult, probably impossible, I think, to apply the idea of disorder of particles to understand the increase in entropy as the temperature of a solid increases. As particles get excited to higher energy levels, the vigorousness of their vibrational motion increases. But can we identify this as an increase in disorder of those particles? Probably not. If so, it seems essential to understand it in terms of the above Boltzmann analysis and his entropy equation. In that case, the disorder of particles offers only an incomplete understanding of entropy. The following is the third fundamental characteristic of Boltzmann distributions that becomes evident when we contrast the results in table 1 for lead and table 3 for silver reproduced here in this table. At 50 Kelvin, only the lowest 3 levels are occupied for silver, whereas the lowest 6 levels get occupied for lead. At 100 Kelvin, only 5 for silver, but 12 for lead. And at 150 Kelvin, only 8 for silver, but 19 for lead. Why? Recall that the vibrational frequency of silver atom is 4.48 times 10 raised to 12 per second, and that of lead atom is only 1.83 times 10 raised to 12 per second. Thus, it is higher for silver. As seen in part 1a, since the energy level gap is 1 quantum equal to h nu, it is larger in silver than in lead. Hence, silver atoms require more energy to get excited to higher levels than lead atoms do. That is, it is harder to excite the silver atoms than the lead atoms to higher levels. But only the same average kinetic energy is available in the surroundings at any given temperature for both silver and lead, because as per the third postulate of kinetic theory of matter mentioned in part 1a, temperature is a measure of the average kinetic energy of motion of particles. Therefore, the degree of excitation is less in silver than in lead. That is, the number of higher levels to which the silver atoms are excited is less than that for the lead atoms. As a result, N0 in silver is larger and the other Ni's are smaller than in lead. This consequence with respect to silver versus lead is exactly similar to that discussed under fundamental characteristic number 1, namely lower versus higher temperature. As explained there, this in turn results in smaller W and hence lower S for silver than for lead, as seen in tables 4 and 2 reproduced in this table. For example, at 50 Kelvin, W equals 1.554 times 10 raised to 24,135 for lead, whereas it is only a much smaller value, namely 2.374 times 10 raised to 3,152 for silver. At 50 Kelvin, S equals 55,753 K for lead, while it is only a much smaller value, namely 7,259 K for silver. It seems impossible to apply the idea of disorder of particles to understand all of this. It is experimentally known that at 298 Kelvin, HF, HCl, HBr, and HI have the following standard molar entropies Sm0 in joules per Kelvin mole respectively: 174, 187, 198, and 206. They are all in the gaseous state at the same temperature and pressure. Why do their entropies increase in that order? Can the disorder of particles increase in that order? Anyone might say that the degree of disorder has to be about the same for all four substances. Then why are the Sm0 so different? Yes, the only way to explain the above facts is by resorting to a proper Bottzmann analysis and applying his entropy equation. In the gaseous state, the above molecules execute long-range translational motion all the time. According to quantum theory of the translational motion of a particle in a one-dimensional box of length L, the allowed translational energy levels have energies given by n squared h squared over 8m L squared, where n is the translational quantum number that takes only the allowed integral values 1, 2, 3, etc. And the energy gap between the n plus first level and the nth level is given by 2n plus 1 times h squared over 8m L squared. In both equations, one can notice that the mass of the particle appears in the denominator. The same applies to a three-dimensional container also. That means the translational energy levels become closer and closer as the mass of the particle increases. The mass of the molecule increases in the order HF less than HCl less than HBr less than HI. Therefore, in HI they are the closest and in HF they are the farthest. Similar to the case of lead versus silver, as the energy levels become closer, a greater number of molecules get excited to higher energy levels at any given temperature when a specific given amount of average kinetic energy is available in the surroundings. Therefore, the smallest degree of excitation takes place in HF, leading to the lowest value for Sm0, and the largest degree of excitation takes place in HI, resulting in the highest value for Sm0. Now, let us consider the following standard molar entropies Sm0 at 298 Kelvin in joules per Kelvin mole. CO G 188 and CO2 G 214, NO 211 and NO2 240, CH4 methane 186, C2H6 ethane 230, and C3H8 propane 270. Why do these sets of molecules show a similar trend with respect to their SM0 values? Here, in addition to the mass of the molecule, another important factor plays a more prominent role in determining the value of SM0. It is the number of degrees of freedom of motion, that is, the number of sets of energy levels in one molecule available for excitation. A single atom executing motion in a container can only translate in space. It cannot rotate or vibrate. And it can translate in any one of the three dimensions x, y, and z. If it translates in any other direction, we can resolve it into the corresponding x, y, and z components. Thus, we say it has 3 degrees of freedom of translational motion. The number of degrees of freedom of motion is always conserved in nature, meaning it cannot be created from nothing nor be destroyed into nothing. Therefore, when n atoms combine together and form one molecule, the total number of degrees of freedom of motion available for that molecule is 3 times n. Any molecule always has 3 translational degrees of freedom. A linear molecule like CO or CO2 has 2 rotational degrees of freedom, since the rotation around the nuclear axis is a spinning motion and not considered to be a rotational one. The rest, namely 3n minus 5, is its vibrational degrees of freedom. For a diatomic molecule, which is always linear, there is 1 vibrational degree of freedom, and the 2 atoms move toward each other and then move away from each other continuously, constituting a stretching vibration. A non-linear molecule, on the other hand, has 3 rotational degrees of freedom, since there is no specific nuclear axis for the molecule as a whole, and the rotation around the third axis is actually a rotational motion and not a spinning one. Therefore, translation and rotation together account for a total of 6 degrees of freedom for any nonlinear molecule, and the rest, namely 3n minus 6, is the molecule's vibrational degrees of freedom. Accordingly, the number of vibrational degrees of freedom in CO is only 1, and that in CO2 is 4. Thus, the total number of sets of vibrational energy levels is greater in CO2 than in CO. At high enough temperatures in CO2, excitations can take place in all 4 different sets of vibrational energy levels, whereas in CO, the excitations can take place in only 1 set. Therefore, W is larger and hence SM0 higher for CO2. Similar is the situation in the other two sets of molecules. Thus, as the number of atoms of the same kinds increase in one molecule, Sm0 also always increases. In this case also, the idea of entropy being a measure of disorder of particles cannot help one understand why Sm0 changes the way it does. In addition to the disorder of particles, two other simple interpretations of entropy came into vogue. In 1949, Edward Guggenheim advocated that entropy is a measure of the extent of energy dispersal or spreading out of energy in a given system. As the total energy of a system disperses more and more, its entropy keeps increasing. Today, there are several supporters of this idea. This idea stems from the idea of particles being excited to higher and higher energy levels. If all the particles stay at the lowest energy level, as in the case of a solid at absolute zero of temperature, then energy is looked upon as concentrated or localized there. When particles get excited to higher energy levels at higher temperatures, energy is looked upon as dispersed or spread out or delocalized. In other words, it is spread out among a larger number of energy levels instead of being concentrated among a smaller number of energy levels. This same idea of dispersal is then applied to the case when particles spread out into a larger amount of space as during the expansion of a gas, since the energy possessed by those particles can be considered as being dispersed over a larger volume. Thus, this qualitatively explains the increase in entropy as the temperature or the volume of a system of particles increases. Yet another interpretation is that entropy is a measure of the freedom of motion of particles. Its origin is similar to that of disorder of particles. The particles in a solid are restricted in their motion to just vibrational motion, which takes place over a small amount of length. When the solid changes to the liquid state, they execute short-range translational motion. In other words, the freedom of particle motion increases somewhat. When the liquid state changes to the gaseous state, the particles are able to exhibit long-range translational motion throughout the container, implying a much greater degree of freedom of motion. The known increase in entropy from solid to liquid to gaseous states of any given substance is then taken to be due to the increase in the freedom of motion of the constituent particles. This idea can also be employed to understand the decrease in entropy whenever atoms combine together to form a molecule or a formula unit. For example, consider two individual hydrogen atoms in a container. Each one is free to translate anywhere in the container. Now, let us say they bond together to form one H2 molecule. Whenever one hydrogen atom goes, the other has to necessarily follow suit. The second one has lost the earlier translational freedom of motion that it possessed. In fact, as mentioned earlier, it changes into rotations and vibration, which are more restrictive in nature than translation. Thus, this idea qualitatively explains why entropy decreases during bond formation. A more precise reason for this decrease is discussed using Bottzmann entropy equation in part 2 of this video series. And as in the case of disorder, it is completely wrong to just state that entropy is a measure of freedom by omitting the role of particles. If there is a greater degree of freedom for the people of one country than that of another, it is not correct to say that the former are associated with higher entropy. Again, it is important to keep in mind that entropy always has to do with particles of matter and their distribution among energy levels and in space. Like disorder of particles, neither the freedom of particle motion idea nor the energy dispersal idea can be employed in understanding every situation involving a change in entropy. Several of the examples discussed earlier should illustrate this. Thus, they also constitute only an incomplete understanding of entropy. Disorder of particles, freedom of particles, and energy dispersal are qualitative ways to explain what entropy is wherever they become applicable. They are applicable only in a limited number of scenarios. There have been attempts to make this concept simple enough for easier understanding and application. However, to understand this any further at all, it is essential to invoke Bottzmann analysis and his entropy equation. In their absence, it is not possible to understand these. Stating that energy is dispersed is simply another way of stating that particles get excited to higher energy levels or particles occupy a larger amount of space. If someone asks the question as to why energy dispersal leads to an increase in entropy, the only way to respond is by saying that W, namely the number of microstates, always increases when particles get excited or occupy a larger amount of space, and therefore entropy increases as per S equals KLN W. In fact, energy dispersal is taken to be synonymous with an increase in the number of microstates. And the degree of freedom of particles should be understood in terms of the number of microstates possible corresponding to a given macrostate. The greater the number of ways in which a given task can be performed, of course, we would say that there is a greater degree of freedom. If there is only one way of doing something, then that task is completely restricted. Thus, when the number of possible microstates is 1, entropy is 0. Therefore, stating that entropy is a measure of freedom of particles is only another way of stating that entropy is a measure of the number of possible microstates. In a similar manner, as the degree of disorder of particles increases, the number of possible microstates also increases. As an analogy, and only as an analogy, notice that there is only one way in which a new deck of cards can be stacked together when the specific sequence of cards is exactly specified. However, when the cards are shuffled, as the disorder increases, the number of ways in which those cards can get scattered in space also increases. Thus, Bottzmann entropy equation cannot be avoided at all in order to really understand these simple interpretations of entropy. These are only incomplete ways to understand entropy. No one can claim to have thoroughly understood entropy with the help of these three simple interpretations. Making the above even simpler by ignoring the role of particles can only lead to a misconception of entropy and its wrong applications, as evidenced by Mark Thompson's New Yorker cartoon pointed out in part 1a. As Einstein elegantly put it, everything should be made as simple as possible, but not simpler, lest misconceptions and wrong applications should occur. In part 2 of this video series, we will discuss positional or configurational entropy arising due to the spatial distribution of particles in a container of a given volume, in contrast to the thermal entropy discussed so far in parts 1a through 1c.